Hello, in this video I'm going to work out an example of a classic related rates problem that you see from calculus, first year calculus. And what it is that for some reason you have a ladder that is resting against a wall. I don't know what it's doing there, but it sounds pretty reasonable. Here's a ladder, put that in blue. The ladder's resting against a wall. That's a 10-foot ladder. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at 1 foot per second, so that's down here, this point here starts sliding away, starts moving. If the bottom of the ladder slides away from the wall 1 foot per second, how fast is the top of the ladder sliding down the wall? When the bottom of the ladder is 6 feet from the wall. Okay, now, first of all, what we're going to do is take a look at this, and what we see is that we have a right triangle. And I'll accept the criticism that in my enthusiasm for drawing the wall and the ground, possibly we're losing sight of the main important thing, that there's a right triangle there. Okay, so there's a right triangle, and the hypotenuse is fixed at 10 feet. It doesn't change. But then what I do is I label the sides, the vertical sides y, and the height y, and then the base x. You could do b and h for base and height, but I like x and y. Okay, I mean, that really wouldn't make any difference. And then, so what I have is I try to do a drawing, and when I do the figure of the drawing, I assign variables. And then also I look at some other things which I can put under the heading of given, which is I just want to make a summary of those things that I'm given. And I believe this is good for just solving any word problem, is write down what you're given, maybe translate some of this stuff, some of the information given into math language, in this case calculus language. The bottom of the ladder slides away from the wall at 1 foot per second. So the clever thing about this, it's not as if I thought of this clever thing, but if we label the length of the base as x, what we see is that if this point is moving away from if the bottom of the ladder is moving away from the wall, then x is increasing. And so what I'm going to write down is dx dt, the rate of change of x with respect to time is 1. Sometimes I feel like doing the units, sometimes not. S is seconds, all right? So 1 foot per second is the rate of change of x. And because x is expanding, x is increasing, we write it as positive 1. If the base of the ladder were moving towards the wall, if x were decreasing, we would put negative 1, but it's increasing. So that's what we're given. And then I like to also write down what we're trying to find. So we're trying to find, if I have enough space in this little corner here, what I try to find is what? Well, what are we trying to find? How fast is the top of the ladder sliding down the wall? Okay, so when the top of the ladder slides down the wall, what I see is that this variable y is decreasing. So what I'm trying to find, though, is the rate of change of y, how the rate of change of y with respect to time. So at what rate is y decreasing? That will be the same as the rate at which the top of the ladder slides down the wall. So I'm going to find dy dt at the instant when the bottom of the ladder is 6 feet from the wall. So I'm going to find that when x equals 6. All right, so then what I do is I like to write down any type of formulas that can come to mind. And, well, when you have right triangles, you could use trig formulas. Some of the problems have similar triangles, but I would say the go-to one, the very first one that one might consider, probably should, is our buddy, the Pythagorean Theorem, named after Pythagoras, right? So the Pythagorean Theorem gives us a squared plus b squared equals c squared. In this case, we have x squared plus y squared equals 10 squared. So we have x squared plus y squared equals 10 squared. It's important for us to understand that 10 is constant throughout this because we're going to take a derivative. So that's important to understand that 10 is constant. X is changing. X is increasing, y is decreasing as this ladder slides down the wall. Hopefully no one's on top. Okay, so the ladder is sliding down the wall, so y is decreasing, x is increasing. So x and y are not fixed, and they're variable, even though we're going to eventually use x equals 6 as like a snapshot of the photo, of the video, okay? So now what I'm going to do is, what I do in these problems is I'm going to take the derivative of our formula. Now, don't plug in x equals 6 or anything until you take the derivative. And so for our derivative, we are going to apply the derivative with respect to time on both sides of this equation. So we are assuming that x and y both change as time changes. The easy one is the right-hand side, the derivative of 10 squared is 0. On the left-hand side, we have x squared, okay? However, let's just think this through just a little bit. We're going to use, for both x squared and y squared, we're going to use the chain rule because we have as our outside function the function that squares. So when we take that derivative, I'm going to get 2x. The derivative of x squared with respect to x, or the squaring function, is 2 times x. But then the chain rule says I take the derivative of what's inside. And I'll write that as dx dt. By the way, we could use, could call that x prime when I write down dx dt, and I do that pretty often because I'm I don't know, it's a little easier to write x prime than dx dt, but oh well. Okay, we come over here to this y squared. The chain rule says I take the derivative of 2 times whatever's inside, but what's inside is y, so it's 2 times whatever's inside at the first power, that's 2y to the first power, but then the chain rule says I multiply by the derivative of what's inside. See, what we're usually doing when we take the derivative of y squared with respect to y, so then you would get 2y, but this is with respect to t. So we have derivative of y squared, 2y, and then we multiply the derivative side, dy dt. If you were taking the derivative with respect to y, you could multiply by dy dy, but dy dy is 1. Okay, and let's, this is a little tiny step. Sometimes people question me, like, what are you doing there? I'm dividing by 2 on both sides. Why not? Just to make it a little easier to look at. Just to take that in, I'll divide by 2. We don't need, 0 divided by 2 is 0. So we can just do that. Now, I'm moving on to what I call the fill-in or substitute back in. Maybe call it substitute back. But I'm going to fill in the, I'm going to fill in some of those values, some of those things that were given. All right, so what was given here, way up there, is the dx dt equals 1. So I'm going to put in dx dt equals 1. I'm sort of repeating myself. I'm going to put in, I want to find out what's happening when x equals 6, the rate of change when x equals 6. I'm trying to find dy dt. So I don't have anything to fill in for dy dt. I'm trying to find dy dt, but also to fill in, I need to fill in something for y. So I need to sort of take a snapshot when x equals 6. We're going to find y. So actually, you can draw the picture again or not, or just use the formula, which is x squared plus y squared equals 10 squared, but we go ahead and put in x is 6. 6 squared plus y squared equals 10 squared. So you can fill that in and then try to find y. Now, sorry, I wrote that wrong. Just 10, not 10 squared. Okay, by the way, we have something called a Pythagorean triple. 3 squared plus 3 squared plus 4 squared equals 5 squared. That's called a Pythagorean triple. If I multiply everything by 2 squared, if I multiply this equation, okay, first of all, let's go through this. 3 squared is 9, 4 squared is 16. 9 plus 16 makes 25, and that's 5 squared. So this is used so much in word problems, so you just, over and over. If I were to multiply everything by 2 squared, I'm going to get 6 squared plus 8 squared equals 10 squared. Or you can multiply everything by 3 squared, then you get 9 squared plus 12 squared equals 15 squared, etc. But this is the one we're going to use here. And so, see, without doing an algebraic computation, I can figure out what y is. I'm going to get that y is 8 because 6 squared plus 8 squared is 10 squared is something that's a memorized thing because you multiply 3, 4, and 5 all by 2. But, maybe that's not your cup of tea, and so we could also just do this algebraically or do all the steps. So y squared equals 100 minus 36. Doing the steps is completely fine. Y squared equals 64, and we know the square root of 64 is 8. We're only looking for positive roots, so we don't do plus or minus 8 because it's length. So we're looking at length, so we're not going to do a plus or minus on that one. Otherwise, usually we would. When you have y squared equals 64, you do plus or minus. Okay, we're going to put that back over there. So the answer is, to that little sub thing, is that y equals 8. And now I'm going to go ahead and do more snail tracks or whatever we want to call those little tracks down here. Okay, I'm still filling in. Okay, so I'm going to fill in x dx dt plus y dy dt equals 0. And so there's no real reason that I'm rewriting this, except I think maybe you just follow along more easily. Except the problem is my handwriting became messy, and therefore that could cause confusion. It's maybe for that reason, it might be better for me for dx dt to just write x prime, dy dt y prime. But anyway, okay. So as shown here, x is 6. I'm putting in where I see x, I put 6. dx dt, also a little messy here. dx dt is 1. So I'm going to put in 1. Plus y we found was 8. I'll put that in there. And then finally, dy dt is what we're trying to find. Once I put those things in there, it's actually not really dy dt anymore. It's dy dt when x is equal to 6. So that's, but anyway, I'm going to subtract 6 from both sides, and then I'll divide. So dy dt equals negative 6 over 8, so which is equal to 3/4 when x equals 6. So the top of the ladder slides down the wall at a rate of 3/4 feet per second when oh my gosh, it's like I'm writing a little book here. Too much, maybe. When the bottom of the ladder is 6 feet from the wall. And I'm trying to make this going a little faster, so I might have sacrificed handwriting skills there. But by the way, okay, so the thing is, you might say, well, do I really need to do that? Maybe not. Depends on your teacher whether you need to write all that stuff. But anyway, we found that dx dt when x equals 6 is equal to negative 3/4. Isn't that the answer? Why is it negative? Because y is shrinking. Y is getting smaller. Y is decreasing. And so that's where that negative's coming in. That's why it's negative, but instead of putting the negative in my answer, my little essay answer, I decided to say it's going down the wall, so that corresponds to the negative. But you might be completely fine with leaving it like this. Depends on your teacher or something. Okay. The ladder problem, it's a classic. It's in so many textbooks for Calc 1. It's a classic. This one's you can see this as an example, not example. Oh, anyway, just look in any books. They have this. Okay. All right, so that's the answer, and it's hard for me to zoom out and get the whole problem so that you can see it, but okay, it's sliding down the rate at 3/4 foot per second. All right, so that's all. Take care. Goodbye.